we have here 1 molar HCOOH, or formic acid, and 0.1 molar HCOOH. If the percent dissociation of 1 molar is 20%, of course, remember that is based on the Ka. What do you think is the percent ionization if it's a 0.1 molar? Okay, in reality, you would think it should be 20%, right? But in reality, it's a little bit higher than 20%. Let's say 25%. Okay. The reason for that is, notice this is higher concentration, this is lower concentration. If you have a lower concentration, it dissociates better. Okay, so it breaks apart better. And the reason that is because there's more room. Less concentrated, more water around to separate the ions. There is more room for the ions to move. So as concentration of weak acids increases, the equilibrium concentration of H plus increases. Okay, but the percent ionization, so you have more, but the percent as a whole is lower as concentration increases. So the more concentrated it is, the percent gets lower. Okay, so what that means is if you double the concentration of the weak acid, this is 1 molar, this is 2 molar. Does that mean you're going to get twice the amount of the H plus? If this is 0.1 molar, you should get 0.2 molar, right, of the H plus because you have double the concentration. Well, no, you don't. Okay, you actually don't double, but you increase only by a little bit. Okay, and the reason is there's not enough room for all of these ions to come apart. Okay, so they don't all fully come apart as predicted by the Ka. Okay, so let's look over here. Using Ka to calculate the percent ionization, calculate the percent HF ionized in 0.1 molar HF. So you have HF going to H plus and F minus. In the first beaker, you have 0.1 molar. In the second beaker, you have 0.01 molar. So this is 0 initially, 0, 0. Okay, this will dissociate, minus X plus X plus X. This will also dissociate, minus X plus X plus X. Okay, the difference between these two beakers is in the beginning that you have 0.1, this one you have less molarity, you only have 0.01. Okay, so you're going to do, this is X and X, this is 0.10 minus X, this is 0.01 minus X, this is X and X. Okay, so I looked up the Ka in the chart and it's 6.8 E negative 4 for HF. So let me show you the chart in case you've forgotten how to get that. So here's hydrofluoric acid, HF right here, HF, and this is 6.8 E negative 4. And that's where I got the Ka, 6.8 E negative 4. So I write the equilibrium expression, HF, H plus times F minus over HF. This is 6.8 E negative 4. It's equal to X times X, or X squared, divided by, this is E negative 4, that's small enough to make this one negligible. So I'm just going to use 0.1. Okay, I'm going to check that later. So it is, so X is going to be 0.0082. Okay, so the percent ionization is equal to 0.0082 divided by 0.10 times 100. 0.10 is the original right here. Okay, and I got 8.2%. Okay, that's supposed to be less than 5% to be able to do this assumption that it's negligible, which means I have to do this whole thing again using 0.10 minus X here, using the quadratic equation. Okay, so when I use the quadratic equation, just do it again here. So when I use the quadratic, I plug in this equation, 6.8 e negative 4 equals x squared. Since I can't use that assumption, I have to put 0.10 minus x. I'm going to use the quadratic. I won't show that here. But when I use the quadratic, I got x is equal to 0.0079. Okay, and if you compare this 0.0079 to this, it's not that much different. It's just so small. Okay, so the percent ionization here is 0.0079 divided by 0.10 times 100. You have a 7.9% ionization. Okay, so this is when I put 0.1 molar of HF in water, I will get 7.9% of it breaking apart and into the ions H plus and F minus. Now do the same exact thing on this side. Okay, so plugging into the same equation, Ka does not change here. 6.8 e negative 4 is equal to x squared, again, x times x divided by 0.01 minus x. And x is equal to 0.0026, considering if this is negligible, right? I got that as x, and percent ionization is equal to 0.0026 divided by original's 0.01 times 100 is equal to 26%, okay? And notice it's above 5%, so I have to use the quadratic equation again. So doing it again, 6.8 e negative 4 is equal to x squared 0.01 minus x. Use the quadratic, I got x is equal to 0.0023. 0.0023 molar. The percent ionization is equal to 0.0023. This is using the quadratic to get this number right here. 0.0023 divided by the original, which is 0.01 times 100 is equal to 23% ionization. So what does this all mean? What this means is this. You have the same substance, it's HF. Okay, HF dissociates, you use the same Ka, but because the percent is based on the original, the 0.1 and the 0.01, the one with the 0.01 dissociated more. And the reason it dissociated more, you don't get more of it, you get a higher percentage of them breaking apart. This as a compared to the original. You get a higher dissociation because if the molarity is lower, there is more room in the water and the HF wants to break apart more than compared to if you have so much ions in there, this is what, 10 times more, then it won't break apart as much. Okay, so the take-home story is dissociation is better at lower concentrations, and this proved that to you. At higher concentration, it was 7.9%. At lower concentration, it was 23%. This is at high concentration, and this is at low concentration. Percent ionization is better. Okay, why is that? Diluting from 0.1 to 0.01 caused the equilibrium to shift to the right. If this is the reaction, it made it shift to the right, the ionized form. Why is this? Dilution, or that's another word for watering it down, causes the reaction to shift in the direction of larger number of particles. So if you add more water, you're going to get more particles of the ions breaking apart. Because this counters the effect of decreasing concentration of the particles. Since you have less in the beginning, it wants to make more.